fundamental purpose of an armored reconnaissance vehicle is to see without being seen, to gather critical battlefield intelligence, and to slip away before the enemy can bring overwhelming firepower to bear. This doctrine relies on stealth, agility, and a high degree of situational awareness provided by an unburdened, focused crew. Yet, in one of the most baffling and catastrophic procurement failures in modern British military history, the Ministry of Defence managed to procure a stealth scout vehicle that was so violently loud it could be heard from kilometers away, and so violently unstable that it systematically destroyed the hearing and the joints of the very soldiers operating it. This is the story of the Ajax Armoured Fighting Vehicle, a £3.2 billion project that morphed from a theoretical triumph of modular engineering into a bureaucratic nightmare of sunken costs and ignored warnings. The Ajax was meant to be the digital eyes and ears of the 21st century British Army, a massive leap forward from the aging Cold War platforms of the late 20th century. Instead, it became a textbook example of what happens when ambitious technological requirements collide head-on with the brutal, unforgiving laws of physics and a procurement culture entirely divorced from operational reality. If detailed technical breakdowns of military history and British combat engineering interest you, subscribe. I've got more of these coming. To understand how the British Army ended up with a reconnaissance vehicle that actively harmed its own crews, one must first look at the aging machines the Ajax was designed to replace. Since the 1970s, the British Army had relied on the Combat Vehicle Reconnaissance Tract, widely known as the CVRT family, which included the highly successful Scimitar light tank. The CVRT was an absolute marvel of its era, engineered with a lightweight aluminum hull that kept its weight down to a mere 8 tons. It was so light that it exerted less ground pressure than a fully equipped infantryman, allowing it to traverse boggy terrain, deep snow, and treacherous mud that would instantly swallow a main battle tank. Powered initially by a commercial Jaguar automobile engine, the Scimitar was incredibly fast, remarkably stealthy, and saw extensive, highly successful combat from the Falklands War to the Persian Gulf in 1991. However, by the dawn of the 21st century, the CVRT was desperately showing its age, offering virtually no protection against modern threats like improvised explosive devices or heavy infantry anti-tank weapons. The aluminum armor that gave the Scimitar its legendary mobility was tragically inadequate in the asymmetric urban combat environments of Iraq and Afghanistan, where underbelly mine blasts and rocket-propelled grenades were the primary threats. The British Army recognized that it needed a replacement, sparking a multi-decade saga of failed procurement programs, starting with the aborted Anglo-American Tracer program in the late 1990s and culminating in the highly convoluted Future Rapid Effects System, or FRES, program. The Future Rapid Effects System was intended to be a massive, interconnected family of medium-weight vehicles that could be rapidly deployed globally by air, striking a perfect balance between heavy armored survivability and light infantry mobility. This theoretical perfection, however, was a strategic illusion, as the Ministry of Defence repeatedly altered the requirements, shifting the focus from rapid air transportability to heavy armor protection, as the casualty lists from Middle Eastern counterinsurgency operations continued to grow. Eventually, the FRES program collapsed under the weight of its own contradictory requirements, but the desperate need for a reconnaissance vehicle remained, leading the Ministry of Defence to salvage the Scout vehicle component and rebrand it as the Specialist Vehicle Program. Instead of designing a bespoke hull from scratch, the ministry opted for what they believed would be a safe, off-the-shelf solution by selecting the ASCOD chassis, designed by General Dynamics European Land Systems. The Austro-Spanish Cooperative Development, or ASCOD, was originally conceived in the 1990s as a standard infantry fighting vehicle for the Spanish and Austrian armies, where it served adequately in the 15 to 30-ton weight class. It was a conventional, highly functional chassis designed to carry infantry to the front line, but the British Ministry of Defence looked at this standard infantry carrier and decided to transform it into the most heavily armored, sensor-packed reconnaissance vehicle the world had ever seen. This decision to heavily modify a pre-existing medium-weight chassis was the first critical link in a chain of catastrophic engineering compromises. The British Army demanded that the new Ajax vehicle possess unprecedented levels of modular armor to protect the crew from the devastating improvised explosive devices they had encountered in the Middle East. They mandated the integration of a V-shaped underbelly blast plate, thick composite side skirts, and heavy modular armor packages that caused the weight of the vehicle to skyrocket from the original ASCOD's 30 tons to an astonishing 42 tons for the Ajax variant. To put this into perspective, 42 tons is heavier than many Cold War-era main battle tanks, including early variants of the Soviet T-72. Yet this enormous mass was being applied to a suspension and drivetrain architecture originally engineered for a significantly lighter machine. The engineers at General Dynamics were forced to uprate the MTU V8 diesel engine to produce 800 horsepower just to move this immense bulk, while simultaneously reinforcing the torsion bar suspension to prevent the hull from bottoming out under its own weight. This heavy armor protection solved the immediate strategic requirement for crew survivability against mine blasts, but it introduced a severe structural penalty, fundamentally altering the center of gravity and the resonant frequency of the entire hull structure. Despite these underlying weight issues, the Ministry of Defense pressed forward, captivated by the highly advanced offensive capabilities that were being integrated into the Ajax turret. The centerpiece of the vehicle's firepower is the revolutionary CTA International 40mm cannon, a weapon system that represents a genuine masterpiece of modern ballistic engineering. Unlike traditional cannons that use standard brass casings trailing behind the projectile, the CTA uses case-telescoped ammunition where the projectile is completely encased within a cylindrical tube of propellant. This creates a remarkably compact soda can-shaped round that takes up significantly less volume inside the cramped confines of an armored vehicle, theoretically allowing the Ajax to carry a larger combat load while minimizing the inboard footprint of the gun mechanism. The breech of the 40mm gun is equally ingenious, utilizing a rotating cylinder mechanism rather than a traditional sliding block breech. The automated feed system pushes a fresh case-telescoped round directly into the rotating chamber. The chamber then pivots 90 degrees to align with the barrel, fires the projectile, and rotates again to allow the next incoming round to physically push the spent casing out the other side. This push-through mechanism is incredibly space-efficient and allows the gun to elevate to high angles for engaging urban targets or low-flying drones, delivering devastating high explosive and armor-piercing capabilities far exceeding the old 30mm Rardin cannon used on the Scimitar. But this devastating firepower and ingenious ammunition feed required an exceptionally complex turret architecture, completely negating the space-saving benefits of the case-telescoped ammunition. Because the Ajax was expected to act as a frontline intelligence hub, its turret was burdened with an immense array of electronic warfare systems, acoustic shot detectors, laser warning receivers, panoramic thermal optics for the commander, and fully digitized fire control networks. The sheer volume of hardware packed into the turret forced it to become incredibly large and disproportionately heavy, which exacerbated the already critical top-weight issues of the overloaded ASCOD hull. When engineers combine an overloaded chassis, heavily reinforced torsion bars, a massive turret, and steel tracks grinding across the earth, the resulting physics can be highly unpredictable. And in the case of the Ajax, the result was a harmonic disaster. As early prototypes began rigorous field trials at testing grounds in Millbrook and Bovington, crews immediately began reporting violent, uncontrollable vibrations radiating through the whole structure, accompanied by deafening levels of interior noise. The combination of the extra armor weight, the modified suspension, and the specific track tension created an acoustic resonance effect, effectively turning the interior of the 42-ton steel hull into a giant amplifier that directed low-frequency mechanical vibrations straight into the crew compartments. This was not simply a matter of the ride being slightly uncomfortable. It was a severe physiological hazard that fundamentally compromised the combat effectiveness of the vehicle and the safety of the soldiers inside. When a heavy armored vehicle experiences unmitigated harmonic resonance, the vibrations travel through the floor plates, up through the mounting brackets of the crew seats, and directly into the skeletal structures of the operators. Prolonged exposure to this specific frequency of intense, low-level vibration causes severe health issues, including swollen joints, localized nerve damage, profound nausea, and a condition known as vibration white finger, which severely impairs a soldier's ability to perform fine motor tasks like operating complex digital touchscreens or fire control joysticks. Furthermore, the noise levels generated by the grinding drivetrain and the resonant hull vastly exceeded the legal and medical limits set for military personnel, peaking at decibel levels that standard issue noise-canceling headsets were completely unable to suppress. The sound waves were so intense that they resulted in bone-conducted acoustic trauma, meaning the deafening roar of the vehicle was bypassing the crew's ears entirely and traveling through their skulls directly into their inner ears. Knowing what you now know about its real-world survivability and reliability, would you still want to be stationed in this machine during combat? Share your thoughts below. The human toll of these engineering failures was both immediate and tragic, completely shattering the illusion of the Ajax as a next-generation battlefield asset. During the testing phases, dozens of highly trained British Army vehicle testers and crew members suffered documented hearing loss, chronic joint pain, and severe acoustic trauma, with some personnel eventually requiring medical discharge from the armed forces due to the permanent damage inflicted by their own vehicle. The vibration was so violent that it not only broke the bodies of the crew, but it also physically shook the advanced electronics to pieces, causing delicate thermal sensors to fail and making it entirely impossible for the gunner to accurately track targets or fire the 40mm cannon while the vehicle was on the move. An armored reconnaissance vehicle that cannot fire on the move, cannot use its sensors effectively while driving, and cripples its crew before they even reach the line of departure is functionally useless in a combat scenario. By the end of 2020, the severity of the crisis forced the Ministry of Defense to halt all live trials, imposing a humiliating 20 km/h speed limit on the few prototypes that were allowed to move, and strictly forbidding crew members from remaining inside the vehicle for more than 90 minutes at a time. The most infuriating aspect of the Ajax disaster was not the engineering failure itself, but the institutional culture of denial and bureaucratic inertia within the Ministry of Defense that allowed the crisis to spiral out of control. Subsequent independent investigations, most notably the scathing Sheldon report, revealed a deeply entrenched culture of optimism bias and departmental siloing within the Defense Equipment and Support Organization at Abbey Wood. The report explicitly detailed how early warnings from frontline soldiers, testing personnel, and the government's own defense science and technology laboratory regarding the dangerous noise and vibration levels were systematically ignored, minimized, or dismissed as minor teething troubles. The procurement executives, desperate to keep the £3.2 billion project on schedule and avoid political embarrassment, continuously pushed the program forward, effectively silencing the safety concerns of the end users in favor of maintaining contractual momentum. This catastrophic disconnect between the bureaucrats managing the budget and the soldiers enduring the physical reality of the machine highlights a fundamental flaw in modern defense procurement, where the sunk cost fallacy dictates that a project deemed too big to fail will simply be funded indefinitely, regardless of its operational viability. When placed in a comparative context against rival nations' hardware, the absurdity of the Ajax development cycle becomes even more glaring. The Swedish military, for instance, successfully developed the CV-90 family of armored vehicles, which continually evolved over 3 decades from a light infantry fighting vehicle into highly specialized, heavily armored variants without crippling their suspensions or deafening their crews. The Swedes achieved this through iterative, ground-up engineering, ensuring that any increase in armor weight was met with a corresponding fundamental redesign of the whole geometry and suspension architecture, rather than simply bolting extra mass onto an older frame. Similarly, the United States Army continuously upgraded the Bradley M2 fighting vehicle, adding explosive reactive armor and modernized sensors, but they always remained acutely aware of the platform's absolute weight limits, eventually initiating entirely new vehicle programs, when the Bradley could no longer support additional mass. The British Ministry of Defense, conversely, attempted to bypass the time and expense of iterative engineering by forcing an excessive list of bespoke, contradictory requirements onto a pre-existing commercial chassis, vainly hoping that brute force horsepower and complex electronic systems could overcome fundamental structural imbalances. Faced with mounting public scrutiny, the threat of project cancellation, and billions of pounds already spent with 0 deployable vehicles to show for it, General Dynamics and the Ministry of Defense were forced into a frantic, highly expensive redesign phase to salvage the Ajax. Because starting over was deemed politically and financially impossible, engineers had to apply complex, retrofitted bandages to mask the underlying harmonic issues of the overloaded hull. They introduced specialized dual-layer acoustic dampening headsets with integrated throat microphones, requiring crews to wear essentially double the ear protection just to communicate over the internal roar of the drivetrain. The rigid crew seating was entirely ripped out and replaced with highly advanced energy-absorbing blast seats mounted on sophisticated vibration isolation dampeners, designed to physically decouple the human body from the violent shaking of the hull floor. Furthermore, structural modifications were made to the track tensioning system and the idler wheels, while extensive acoustic paneling was layered into the interior crew compartments to desperately absorb the low-frequency resonance. These mitigations, while technically functional, added even more weight and complexity to an already overloaded system, creating an environment where the crew is merely insulated from the vehicle's structural flaws rather than the flaws being actually cured. The operational reality of deploying a massive 42-ton scout vehicle in future conflicts raises serious questions about the strategic doctrine of the modern British Army. The original C-T Scimitar survived by being highly maneuverable, utilizing its low profile and featherweight ground pressure to hide in tree lines, cross weak civilian bridges, and rapidly relocate before enemy artillery could zero in on its position. The Ajax, by contrast, relies almost entirely on its heavy armor and advanced sensor suite to survive, adopting a doctrine that assumes the vehicle will inevitably be detected and struck, and therefore must be able to absorb the blow. But a 42-ton vehicle has a massive thermal and acoustic signature, requires heavy engineering support to cross standard European bridges, and is completely dependent on intense logistical supply lines for its heavily specialized case-telescoped ammunition and high-maintenance electronic networks. If the vehicle's electronic architecture fails in a damp, muddy, electronically contested environment like the plains of Eastern Europe, its massive weight and wide profile transition from being heavily armored assets into severe tactical liabilities, trapping a deafened crew inside a highly visible, sluggish bunker on tracks. Field maintenance for the Ajax presents an equally daunting challenge for the frontline mechanics of the Royal Electrical and Mechanical Engineers, who must keep this overly complex beast functional in austere environments. Unlike the older generations of armored vehicles, where a mechanic with a wrench and a manual could reasonably diagnose and repair a broken suspension arm or a fouled breech, the Ajax requires highly specialized digital diagnostic tools merely to clear fault codes generated by its myriad integrated sensors. The 40mm CTA gun, while brilliant on the test range, utilizes a highly intricate ammunition feed mechanism with extremely tight engineering tolerances, making it highly susceptible to the ingress of dirt, sand, and saltwater spray inevitably encountered during expeditionary deployments. If the vibration isolation mounts degrade under the constant strain of cross-country movement, or if the intricate wiring harnesses that connect the turret sensors to the hull fire control computers are damaged by internal friction, the vehicle must be entirely withdrawn from the front line for depot-level repair. This heavy logistical footprint stands in stark contrast to the original concept of a rapidly deployable, easily sustainable reconnaissance force, proving that adding immense technological complexity often drastically reduces actual battlefield availability. Despite these glaring fundamental flaws, the delayed entry into service and the billions of pounds wasted on bureaucratic mismanagement, the Ajax will ultimately enter service with the British Army, largely because there is simply no remaining budget to procure an alternative. It will stand as a formidable machine in terms of raw sensor capability, boasting thermal optics and digital battlefield integration that genuinely outclass most adversary systems currently deployed by the Russian military. The 40mm case telescope gun, when it is functioning correctly and the vehicle is stable, delivers a level of devastating kinetic energy and programmable airburst capability that makes it highly lethal against enemy infantry fighting vehicles and heavily fortified urban positions. But these technological triumphs will forever be overshadowed by the fundamental compromises of the platform, serving as a permanent rolling monument to a procurement system that prioritized theoretical specification sheets over the physical realities of combat engineering and human endurance. The legacy of the Ajax program extends far beyond the technical specifications of its armor layout or the acoustic frequencies of its hull resonance. It is a profound lesson in the dangers of strategic arrogance and the sunk cost fallacy. It demonstrates exactly what happens when defense contractors and government bureaucrats convince themselves that advanced software and raw horsepower can paper over the fundamental laws of structural physics and weight distribution. The soldiers of the British Army will eventually learn to operate the Ajax effectively, developing intricate tactical workarounds and enduring the logistical headaches because frontline troops have always had to adapt to the flawed equipment forced upon them by peacetime administrators. But the vehicle that was supposed to be the undisputed vanguard of a highly agile, digitized military force will instead limp into service over a decade late, heavily modified, compromised in its core design, and serving as a deafening reminder of how not to build an armored vehicle. If you found this analysis useful, a like helps more people discover these deep dives. Thanks for watching.